We're going to be hearing from David Malcolm of Red Hat. He maintains Python on Fedora, and he'll be have a talk called "Dude, Where's My RAM?" A deep dive into Python, how Python uses memory.
Thanks very much. Hopefully you can hear me. So I'm going to be talking about Python memory usage, and in particular CPython memory usage, perhaps a little bit of PyPy, and ways you can measure where the memory is going. So, for example, top, which is a pretty bad way of looking at memory usage, and where your memory might be going. So this is totally going to be a complete incomplete tour of this topic, because it's huge, and so it's going to be somewhat a bit of the express tour. So how it's done, it's also in the extreme category of talks, so I probably shouldn't be giving you all this fluff. But yeah, some of the problems, some of the fixes, and how you can track it. And in particular, I'm going to be focusing on a new tool that I've written, which is an extension to the GNU debugger, GDB, called GDB heap, and that's the URL there. On Fedora hosted, and it's basically a new. Well, I'll tell you what it is in a bit. So, types of memory usage problems. There's the simple. My Python program is just too big. The workload's too big, or it's an ongoing thing that changes with time. So the memory usage might start at an acceptable level, but then over time it gets bigger and bigger and bigger. Now that could be an ongoing leak that is just going to continue to get worse. Or it could be some kind of what I call a high watermark, where it gets worse and then it kind of doesn't get worse anymore, and it reaches a level of badness, but it never gets any worse than that. And then there's also just the fact that if you have a lot of CPython processes on your computer, they don't do a very good job of sharing memory between them compared to other technologies. So those are the symptoms. Why does this happen? If you're just using too much memory, well, maybe you need a better representation for your data. There are a couple of, the classic one everyone knows about for memory leaks is if you screw up reference counting in extension types. There's another one that's less known about, which is if you implement a C extension, a type in a C extension module that owns references on other objects, you have to implement the TP traverse, I think it's called callback, in order to properly integrate with the garbage collector. And if you get that wrong, well, if you get it wrong, you can segfault the process. But if you get it wrong in other ways, you can make the garbage collector just fail to work, and you can have dead self-referencing cycles of objects that never get collected. There's the kind of high watermark behaviors that typically mean you've got too much caching going on. And that can either be in your own PY in the Python code, or it can be in one of the layers below, perhaps in CPython itself, or perhaps in one of the libraries that you've wrapped in C code. And it can also be heap fragmentation, which you perhaps can think of as an example of the same thing. And the lack of sharing, the trouble with CPython is even operations you might think of as being read-only, like an attribute access, you're constantly twiddling the reference counts on all these objects, which makes it very hard for an operating system kernel, or indeed a hypervisor running multiple operating system kernels, to do a good job of sharing pages that ought to be identical. Like you fork a process, but the pages very, very rapidly become non-equal. Okay, so fixes of these problems, yes. Use better data representations, fix your bugs, evict your caches, and use PyPy. PyPy did a great talk yesterday where they spoke a lot about their just-in-time compiler, but what they didn't talk about was the flexibility of their engineering approaches meant they can be able to experiment with all kinds of new representations for things like the fundamental data types in Python. And so, and that's already leading to, well, I believe, big memory usage savings. So it's not just the speed-ups, it's potentially memory savings as well. So let's do a bit of a dive through the abstraction layers. So here's a fragment of Python code, a really bad US-centric address class with 6 string fields. And let's make an instance of it, assign it to variable A. So going down an abstraction layer, we have the globals dictionary, which in the top left, which references, has key A, which is a reference to an instance of an address, which references the address type, which has a reference to its done-to-dict, which is a dictionary in the middle, which has references on the left-hand side to all its keys and to all its values. And then One level below that is, that's kind of at the object level, is at the level of allocations in CPython. So if we focus on the middle, you'll notice that the dictionary has actually been implemented with two different allocations. For the object itself and for a table, internal bookkeeping table, mapping keys and values with hashes. And so that's two allocations at that level, assuming the dictionary is big enough. And how do you measure at that level? Fighting my thing here. In CPython 2.6, sys.getSizeOf was added, which is basically how you pointed at an object, say, how big is this in bytes? And exactly what that means, there's some debate, you could debate what the actual meaning of that is. And what it kind of means is how big is this object and any buffers that are used by the direct internals of this object, but don't count the objects that this object references and thus keeps alive. And it works for all the built-in types, and it might work for a C extension module wrapper object, but it might not. And there's kind of no really good way of then saying, well, we dive down into the C or C++ space, and there's a whole graph of pointer references going on there, and yeah, we wave our hands, and that's difficult. So yeah, here are the actual sizes. And I'm not going to dwell on this, the thing that's most interesting to me about this is if you compare the 32-bit build and the 64-bit build, everything basically doubles in size, which kind of sucks, but there's no good way of fixing that without entirely rewriting the implementation. Where are we here? So moving on, dictionaries. For small dictionaries, and this is interesting to me because typical object implementations have a dunderdict, so that the object has a reference to one of these dictionaries, and how big these are can be pretty significant. Between 0 and 5 entries, there's a certain amount, but when you go up to 6 entries, it quadruples in size because it has a buffer that tries to keep 3/4 full, and when it exceeds that certain limit, it goes to that level. And then it has to allocate an external buffer, which doubles it, and then it doubles it again, and well, so there's an interesting quadrupling when you reach that first threshold, and then it doubles at successive thresholds. So I did a really bad benchmark, and this slide is a complete lie, in which what I did was I wrote a loop and I created 10,000 instances of my rather simplistic address class that I showed you before, and measured the memory usage of, okay, start up Python or CPython 2.6, 64-bit, and create 10,000 instances using several different representations. So I started with as an old-style class, and it took 12 meg of RAM. Okay, well, the other caveat I should put up and say why this measurement is a lie is that I gave all of the values for all of these instances are shared by all the values. So all this is measuring is the bookkeeping cost of the objects and not of the values of those attributes. So an old-style class was 12 meg, a new-style class was slightly cheaper. By simply storing a dictionary and not having the class at all, there's a fairly big saving. And then the big savings are just saying, let's have a tuple and let's maybe give it some syntactic sugar by using collections.namedTuple. And that's a pretty big saving, but the problem with those two approaches is your data suddenly becomes immutable because tuples are immutable. And then finally, if you add the dunder slots optimization, if you compare the new style class row with at the bottom, it's basically a 5-fold saving in memory usage. But as I said, this is a lie because all this is measuring is the overhead cost of the storing what the attributes are for the object as opposed to storing what the attributes' values are. That makes sense. And so depending on exactly how we assign the values, we could arbitrarily stretch this graph to minimize the differences. So exactly what the benchmark should be, I don't know, and good benchmarks are most welcome. And in case you don't know the dunder slots optimization, you add a dunder slots where you list into a class scope, where you list the names of the attributes that an instance can ever have. And it'll raise an attribute error if you go outside that, unless you list dunderdict within it. And the good news if you're using PyPy is PyPy does all this automatically for you, and you get the saving, and it's great. So look at PyPy. So if you've got a memory usage problem where the memory usage is simply at the Python level, and you have lots and lots of Python objects, and you want to keep track of, well, why are all these objects alive and where the memory usage is going, one of the canonical engineers created a tool called Meliai, if that's how it's pronounced, or Meliai, I don't know. I think it's an anagram of his name, which I think it was for use in doing memory optimization on BZR, or however that thing is pronounced. And what it does is it walks the, and there's a few tools in this space, and this seems the most advanced to me. It walks the garbage collector metadata, keeps track of all the objects that are, the garbage collector knows about, and walks the reference graph and dumps it in JSON form. It basically has optimized C code that can then dump all that as a JSON file, and then has a bunch of tools for carving that up and querying it and figuring out, well, what is the reference chain that's causing the bloat? And that's pretty cool, if your problem is at that abstraction layer. But if we need to go below that layer of an object reference graph and the allocations in the built-in types, how do we do that? Well, basically there's a Python allocator. Allocations of 2567 bytes and above go directly to the operating system's malloc routine. For small allocations, there's this PyMalloc allocator, which carves up 256K blocks of RAM that then get carved up further into 4K pages that and there's a whole bunch of bookkeeping going on in there. So there's a whole bunch of optimized allocations for small allocations going on. Ultimately, though, everything goes down into malloc for the operating system. So we have to say, well, how is malloc implemented? And in the GNU standard C library, it uses the classic boundary tags implementation, which you can, if you have a copy of Knuth, you can read it in volume 1. And there are multiple large regions which are maintained by the operating system. We're using the SBrook and mmap syscalls on a POSIX system, or maybe Linux, whichever. And there's basically a doubly linked list of, within those, of free and used blocks. And if you naively look at the memory map of a process in Linux by looking at, say, /proc process ID maps, you see there's a whole bunch of crazy hexadecimal stuff. And you might look at this and say, heap, that's the memory map for the heap. And that's, unfortunately, is kind of misleading because there's also, right at the bottom here, I highlighted a few areas, but that bottom area there, those things that aren't labeled at all are, in fact, anonymous memory mapped regions that are also being used for the heap. So how do we track down problems when we go down to this layer? Well, Valgrind and similar solutions on non-Linux systems is one way. It's a processor simulator that tracks all memory usage in the simulated process. But it changes the behavior of your program, and it's slow. Well, it's slower than running on the CPU. And you can't attach it to a running program. So I had the issue where I look at something in top on my Linux box, and something is huge, and I think, well, why is it big? And trying to reproduce that behavior. So I created this extension to the GNU debugger GDB called GDB heap. GDB 7 onwards has gained the ability to be scripted using Python. So you can write Python scripts and that know how to introspect data from a crashed process, or just any process you've attached to. And I gave a talk about this yesterday, giving a brief overview of what the API looks like and some ways in which you can use this to help with simple debugging tasks. So basically what I've done is I've written a fairly large body of Python code using this API that understands memory allocation in a process that you're debugging. So it doesn't require any cooperation. You can attach it to a process that you started, for example, some system daemon that you started 3 weeks ago, or to a core dump from a crashed process. So it's, 2,600 lines of Python code. So it has a code to basically introspect and traverse the GNU standard C library's malloc and free implementation, and also understands CPython's optimized allocator on top of that, and how CPython objects are laid out. And I've also got some heuristics for dealing with C++ and the GTK type system, which is another type system written in C. If you've got a process with a bunch of shared libraries, and some are in C++ and some are in C, and you've got a kind of Python glue layer, and then you're doing this might be a good way of analyzing all these different things and figuring out, well, where are all the bytes going? So yeah, it locates the malloc and free implementation, and it basically yields a succession of objects back inside GDB representing the allocations, and then also looks at PyMalloc and sees, if it sees a 256K malloc block, it can say, well, is this one of the blocks that I got that the CPython allocated? And if so, it knows how to carve that up further into both bookkeeping areas and claimed and not yet used and free regions, and walks them. And then it runs a series of categorizers on the blocks of memory that it gets back. And so basically, I have a whole bunch of what I could call heuristics, but which is something of a euphemism for dirty hack, so I try a bunch of approaches where I basically take the block of RAM and say, okay, does this look like a PyObject star? And I do the cast in GDB using Python scripting of GDB, and then look at all the fields and say, well, does this really look like it? Does that reference count look like an integer, or is it insane? Does this look like a pointer to memory, or is it insane? And I apply a set of filters, and for example, I look at the type, I then follow the type pointer to look at the type and say, is that sane? And if it is, I can say, I look up the name of the type, and so I can say, this is a CPython object of this type. So for example, with some subtlety for dealing with the way the garbage collector offsets allocations. So I can say, if this, well, that isn't the only filter. That isn't the only criterion that I'm using in there. There's a whole bunch of additional filters. But I can say, this is actually a dictionary. For C++, I look at the top word of the block and say, is this a C++ vtable? And if it is, I say, oh, well, this block is probably a C++ object of that class. And then also, is this a stream of bytes that look like ASCII ending in a 0, that then basically the allocation ends? That's probably a C-style string. So basically, we start with a whole bunch of memory allocations, and we start categorizing them by themselves. And hopefully at the end of that, we've figured out some small proportion of them, or hopefully large proportion, we've categorized. And then we can use those to start categorizing other allocations. So for example, if we know that we have a Python instance object, this allocation, we can say, well, what is its done the dict? We can follow that and say, that's a dictionary. And then follow and say, there's the MA_table field, which is the bookkeeping for the dictionary, and categorize that. But we can categorize it by saying it is the bookkeeping for a done to dict of an instance of this type. And so there's a scoring system depending on exactly whether you encounter the dictionary first in the traversal or the class instance first. And also, I can just look at statically allocated data within libraries and say, there's a PyObject star interned, which is used in consolidating string allocations in CPython, and say, well, what does it point to? Is this one of our blocks? Okay, well, let's just mark that, because that's important. And so here's a screenshot of it in use. So I type heap. This is, I've run Python 2.6, 64-bit, and it starts up. It's stuck. It's waiting on the interactive prompt. It's read site.py and all the rest. And I attach to it in the debugger and type heap. And you'll see that there's a series of categories that it's been categorized into, which domain, which is Python or C++ or C, or there's a few domains that are kind of arbitrary. And then within a domain, there is kinds, and then detail as needed. And then, so you'll see that and then I divide by the amount of, basically sort by the amount of memory descending. So the biggest allocation here you'll see is this 470K of Python strings, and there were 6,000 of them. And the next category going down is bookkeeping for Python dictionaries for 450K. And then the line below that, you'll see that I actually broke out the intern string dictionary as a special case, not to be counted in the above category, because it's 200K all by itself. And that's kind of interesting information. Like, do we want to optimize that, that particular aspect of CPython? I don't know. And then below that, you'll see that I've also broken out in the fourth row Python strings that are in fact bytecode, because I saw a code object. A few lines below, you see there were 647 code objects it saw, which for 80K for the code objects, and then a further 90K, 2 lines above, for the actual bytecode strings themselves. So you see there's a lot of very rich information that we're getting from this, from a completely unprepared debugging session. You'll also see there's a lot of uncategorized, which is none of the heuristics worked, and we weren't able to figure anything out, which kind of sucks. And basically, whenever I'm trying to use this, and this shows high up in the profile, I've got a hex dumper as a hex dump command, and it's like, okay, figure out what's going on there. So it's not a perfect tool. And so basically, if we scroll down through the kind of a long tail of allocations, you'll see there's 16 ABC meta instances, and then below that, here are the bookkeeping for their dunderdicts, another 16 of those. And you'll see in the middle of there's a pool header overhead. So that's marked PyArena, and so that's overhead associated with the optimized allocator. So I really am trying to analyze every single byte in the process being debugged. And the ob item table for implementing the list objects there. And yeah, there's the dictionaries themselves as opposed to the dict entry tables within them. And yeah, alignment wastage. There were 1,000 odd bytes in order to ensure that the pages within the optimized allocator are aligned on a 4K boundary, and so on. So this is very low level. And scrolling all the way down to the bottom, you've got the totals. There were 18,000 allocations split into 2.6 megabytes of data, roughly, depending on whether you're 1,024 or 1,000. I've also entered a query language, so it's like a mini version of SQL or SQL. So you type heap select and then give it criteria. So, for example, select kind equals underscore int block. CPython 2 allocates integers using these 1,000-byte blocks that then get carved into the integers themselves. And so if I query for that, you'll see that there are, 10 or 11 of them? And then here are the addresses and hex dumps, and you can investigate this in detail. Here's a more crazy query where I select kind of string and its byte code, and that the size of the buffer is less than 100 bytes. So I kind of look, here they all are, and now I can, lower on the slide, I actually look at the data and I disassemble the byte code. Although that relies upon, I'm using the version of Python in the debugger, happens to be the same version of Python that I'm debugging, so that the bytecode happens to have the same format. So it's kind of a cheat. And also added instrumentation subcommand heap CPython allocators, which shows that there are currently 3 of these 256K pools allocated, and kind of an idea of the utilization within them. And I guess I can add new stuff as needed if there are any other CPython folks in the audience who want additional tools. So yeah, caveats. It's very low level, and it might be too low level. As I say, all it understands is allocations and pointer references, and it doesn't know about the garbage collector, the object reference graph. You can only categorize what it knows how to categorize. It can categorize about 10,000 allocations per second, which is great on a small process, but if you've got 1 million allocations, it means it's going to take like a quarter of an hour. And yeah, the really ironic thing is it's really memory hungry. And yes, I have pointed it at itself and done some optimization there. But yeah, I'm currently, it's at the stage of useful, needing optimizing prototype that I'm getting useful results out of, but I kind of want the flexibility of pointing it at more types of programs before going really micro-optimizing it further. So a success story. I've been unhappy with how much the memory usage within the Fedora operating system. Our software update is written in Python and then talking to the underlying C library for RPM. And I pointed the tool at that updater and was able to get some very concrete information. Basically, there was a buffer being kept alive at the C level through a chain of pointer references that eventually reaches the Python level, and then the Python objects. And we're basically able to see, that's the problem there. This is being kept alive. And ironically, some caching that was intended to save memory was making memory not get released. So that's being hopefully fixed in our next release. Future plans, I'm getting some requests to to look at the memory usage of long-running web servers, or so I might next teach it about the Apache portable runtime. And if anyone's got ideas for other things, like, for example, making it specific ideas for making it better for debugging CPython, I mean, I'm all ears. And other things you might be interested in, although, I mean, my own passion is CPython. So to summarize, basically, I've given a very incomplete tour of some aspects of CPython's memory wonders. And also, I mean, I've focused very heavily on my own tool because it's new and you probably haven't seen it. But as I said, there are plenty of other tools, so this is kind of a biased account and why I've spent so much time dwelling on this. So depending on which abstraction layer, you might want to look at Valgrind or Meli or GDB heap. So hopefully any questions? Or I don't know how we are for time. 5 seconds, brilliant.
If there are any questions, again, come up to the microphone.
Thank you. This looks like a good tool for an important problem.
Thank you.
You mentioned CPython is your passion or something like that.
Yeah.
And I want to know, have you looked at PyPy, and what do you think about supporting it?
I've actually looked at supporting it. If you point it at a running PyPy instance, you get this big wall of uncategorized. and the reason for that is twofold. PyPy has its own, or at least the default Minimark garbage collector in PyPy has its own arena optimization where it carves out 512K pools of memory with its own thing. And so near the top of the memory profile, it shows there are a bunch of 512K buffers. And therefore, we would need to dive down and look at the allocation there. But then it has its own type system, and where basically I think is at the top of each allocation. Currently, there's a type ID, and it would need logic written in Python and GDB to understand that. But of course, PyPy is written in, well, RPython, and they want to reserve the right to, if they want to completely tear up the implementation details and change it, they've built this toolchain that allows that flexibility. So maybe we could run RPython in GDB somehow and bridge those worlds. And if it's useful, I'm perfectly happy to sit down during the sprints and hack in PyPy support. If the PyPy folks want to do that.
Cool.
Okay, cool.
Okay, thank you. It was an interesting presentation. So I have 3 questions, hopefully short. The first one is, does it work on just Linux, or as long as GDB and CPython, does it work on like Windows?
Yeah, okay. I've only ever tested it on Linux, or specifically Fedora and Red Hat, but I know the GDB hooks work on Ubuntu, say, and so I believe GDB works on Windows, and I know there's GDB on OS 10, but the version of GDB that's in OS 10 is version 6, and apparently, I think, Mac ports has a version of GDB 7, and I don't know if that's been built with the Python support configured in. But yeah, on Windows, you're probably going to have to build GDB yourself, and I don't know. Yeah, that doesn't.
If it's doable, but
yeah,
okay.
I'm sure it's doable. It's an area that doesn't necessarily interest me.
Yeah, sure, but okay, but
forgive me.
it mainly depends on GDB and CPython, basically.
I'm sorry?
It mainly depends on GDB with Python support and CPython, not.
I don't think the underlying Python details would change enough for it to break, but I'm not a Windows expert.
Okay, and I forgot my third question. The second question is. Would it help you to have some like hooks in Python to get more information about the memories? Like, is there something that CPython can do to make it easier to write your tool or not?
That's an interesting question. I mean, CPython already has a ton of really interesting debug things. Like there's a whole debug configuration that you can turn on, which is a compile time setting and breaks ABI because it's an extra pointer at the top of every object. Yeah, I guess so. I mean, the dirty little secret is that I do actually add my own hooks into CPython because I hack on CPython. Yeah, if people have ideas, I'm all ears because I might have not thought of something, and it would be great to add more instrumentation if we can do it without, especially if we can add instrumentation without impacting performance and have it turned on by default. That would be the ideal.
Okay. Okay, thank you.
Martin?
Yeah, I also had the cross-platform question.
Yeah.
Isn't it the case that it would break because the heap walking stops working if you switch to?
Yes, that will completely break.
So would you be interested in supporting Apple's C library, for example?
Which C library?
The Apple OS X C library?
I guess so. If it's something that can be done in a way that doesn't contaminate me from looking at the sources, and I don't know, maybe that's assuming that it's under a license that we can look at in terms of the source code.
I think the C library is published, so
right.
it should be possible to reverse engineer how it organizes the heap.
Yeah, I mean, there is an aspect of looking at the implementation and figuring out what state is visible when we look at this in the debugger that allows us to traverse these data structures, which is sometimes different to the data structure. The data structures aren't necessarily written to be like hacked upon from the outside.
Yeah. But you would be open if
totally,
there are no licensing issues?
Yeah, yeah. I mean, it's under. I can't even. This is really embarrassing. I can't remember what license it's on, but it's. I think I said MIT, but it's a free software license.
Okay. Thanks.
Mm-hmm.
Interesting talk, much in the same direction. Are the memory allocators pluggable? Would it be feasible to support TC-malloc in addition to standard malloc?
Which malloc?
TC-malloc, the one which does a nice job of handling threaded environments.
If I say patch is welcome, does that come across as passive aggressive? No. It's I'm very much
fully familiar with patch
supporting
is welcome, but if you were to say that you never wrote it with plugging allocators in mind.
In terms of the
doesn't
structure
work.
of the code, there's a file glibc.py where I've isolated all the code that's the logic that's specific. Well, I hope I've isolated the logic that's specific to the GNU libc implementation of malloc and free. And then there's a python.py, which is always ironic and amusing, or CPython.py. And there's a pypy.py in one of my trees on that laptop. So, yeah. So yeah, I'm very much open to a tcmalloc.py or if there are other libc implementations, or maybe I don't know what the licensing situation with Microsoft's allocator. That's maybe not something to do in front of 300 people while we're being filmed.
Yep. Thank you.
Thanks.
Thank you, Dave.
Oh.